Okay, Little Schemer Chapter 9. Are you in the mood for caviar? I don't know. Then we must go looking for it. What is looking a lat, where A is caviar and lat is... Okay, let's hide this. What is looking a lat, where A is caviar and lat is 624 caviar 573? Does it return the value, like the number of what you're looking for in the lat? So it'd be number 4? Or maybe number 3 if it uses a 0 index. True. Oh. It just finds whether it's a member. Okay. A is caviar. That's also true. Wait. I was looking a lat where A is caviar. Wait, what? Okay, I'm actually confused. Looking a lat where A is caviar and lat is 624 caviar 573. True. Caviar is obviously in lat. Yes. Looking a lat where A is caviar and lat is 62 grits caviar. They're spelled the same, 573. Were you expecting something different? Yes, I was expecting something different. Does it look for the first word? Yes, caviar is still in lat. Yeah, true enough, but what is the first number in the lat? 6? Yeah. And what is the sixth element of lat? 7? And what is this seventh element? 3? So looking clearly can't find caviar. What? I mean, it didn't, but true enough because the third element is grits, which does not even resemble caviar. So does it stop at the first word? Here's looking. Define looking, a lambda lat, keep looking, a pick one lat lat. Not sure what pick one lat is doing. We did not expect you to know this. Okay. Looking a lat, where a is caviar and lat is yada yada. I think it's true. Because keep looking a 6 lat. Okay, I didn't have this reasoning. Keep looking a 6 lat has the same answer. Keep looking a pick 1 lat lat. I'm not sure I follow. Oh, do the numbers tell it where to look? Pixel 6 lat. I'm really confused. Oh, wait. Okay, so the numbers, I think the numbers tell the procedure, or at least the pick procedure, where to look, what elements to look at, which is maybe why the whole argument is getting passed into, well, no, because something should be recursive. I mean, you at least you need like, even if you need the whole list to look things up in, you still need to keep track of which elements of the list, which number elements you've used already. So see, in this one, caviar is the fourth element, and the number 4 appears in the list of atoms. So I guess at some point it checks this number against the whole list of atoms, one of the procedures, and it finds caviar. It finds a match between the element of the list that's there and the A. But with this, caviar is the fourth element. It's a bit weird how they ask it though. Like they don't go through all the numbers. So my tentative initial guess about how all this works is that the procedures involved use the numbers that appear as the elements of the list to figure out which elements of the lat to check as being possible matches for A. This is consistent. Wait. Oh, son of a gun. Okay. It doesn't go through all the numbers. Now I'm starting to understand. It takes the first number. It starts off with 1. So then it checks the first element. And I'm guessing if it finds a match in the first element, if caviar was the first element, it would return true. If not, it checks if it. So there's 3 possible. The first element is a match for it. The first element is a word that's not A. And there's 3 important possibilities because it could be true, false, whatever. But so the first element is a match for a word that's a match for A. The first element is a number, and the first element is a word that's not a match. Now, if it's a match, or if it's a word that's a match, it returns true. If it's a word that's not a match, it returns false. If it's a number, then it jumps to that point, that element in the list. I'm guessing starting from 1. Like we're counting 1, 2, 3, I mentioned that because sometimes you count from 0. But you start the counting from 1, and then you go to the element of the list. And then you go and you check again. And you run that same task. And you check, is it a match for A? Return true. Is it a word that's not a match for A? Return false. Otherwise, if it's a number, then we jump again. That's why they were jumping around. See, it struck me as weird. I'm like, well, but if they're going recursively, then they should be. And then this didn't really seem recursive either. So I'm like, I mean, it could keep looking, but yeah, there was something weird about it. Okay. Is that the procedures involved use the numbers of the elements of the list to figure out which elements of the lat. Oh, so that was actually okay. I think I figured it. Looking first checks the initial element of the list. If that element is a match for looking returns true. If it's a word that's not a match for A, looking returns false. If it's a number, looking uses that number and then check the element of the list that corresponds to that number, starting from 1, and then runs the same check. Oh, and so then I guess at this point, we could actually find keep say what the arguments are. A, pick, select cell for selection and lat. If A is equal to the selection is a number. I may be jumping ahead here. Wait, is pick? Yeah, okay, so it is a primitive. Okay, so good to recursively caveat. Oh, I need trace looking and keep looking. 624 caveat. Okay, that's no good. 624 caveat. Oh, I typoed. That was all. Wah, 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 wah. There we go. We'll roll. So looking. Yeah. So you can see it follows the same. For this is basically this. We give it the same input. And then it checks 6, and then it checks 7, and then it checks 3, and then it hits grits, and it returns false. And then for the other, first it checks 6, and then it finds a 3. It checks 3, and it finds a 4. It checks 4, and it finds a caviar. It checks caviar, and it finds a. It's pretty straightforward. Pretty straightforward. What is pick 6? Where lat is yada yada. 1, 2, 3, 4. And then 6, 7. When we go to 7th value, when we go to the 3rd value, we find a 4. When we go to the 4th, we find, and that's what, wait, no, hang on. Oops. Okay, scratch that. Because pick just returns the value. There. Yeah, I was mixing up my procedures. So pick 6 lat just goes 1, 2, 3. So it finds value in this lat, which is 7, and it returns that. Yep. Okay. Well, at least I caught it. So what are you asking me? Questions. Oh, let's double back actually. Looking a lat where A is caviar and lat is yada yada. Oh, where A is wait, no, right. And lat. Right. So again, we start out takes us to the 7. 7 takes us to the 3 value, 3, and then 4. Okay, I'm gonna keep looking. A6 lat has the same answer as keep A pick 1 lat. Okay, now I understand. It has the same value because it winds up in the same place. If you call keep looking directly, you going to the 7, you follow this like predetermined path that takes you to caviar. If you invoke keep looking like this, you start out at the 1 at the first, which is a 6, which then takes you to the 6th element, which is a 7, and then you follow the same determined path. So it winds up to keep looking A7 lat where A is caviar and lat. So 7 takes us to a 3, 3, takes us to a 4. 4 takes us to caviar. I'm not sure what I mean by what do we. Okay. Pick. So what is keep looking A3 lat, where A is. So we start out at the third value is 4, so we go to the fourth value and we find caviar. It's the same as keep looking A. Right. This is a little different. So this is. So I'm not sure what Soren stands for, but so, okay. So they don't have a return false. Oh, duh. Yeah. So their structure is basically, if you know it's a number, continue on with a recursive call, which is the same thing that I did, that part. But if you know it's not, just check whether A is equal to Soren, which is their cell. That else is going to return true or false. So I'm going to read A, Soren, keep looking, pick Soren, else equal Soren, looking and keep looking. What else is going to be false? Can you guess what Soren's? Oh, symbol or number. So words? Words or symbol? What is unusual about it? I don't know, bro. Oh, like the base case. Just the map bouncing around based on the input it's provided, one of the arguments, as opposed to just going through it like front to back or back to front or like with the tree method. So there's, yeah. It does not recur on part of lat. Oh yeah, I mentioned that. Yeah, it doesn't recur. We call this unnatural recursion. Oh, it is true. The book is funny. Does keep looking appear to get closer to? I get, like you could easily, like you just give it like A is, and then is like the number 1 and the number 2, and so it starts off in the first one, and then it's like, okay, well I'll go to. That's, I should say. So the default initial value is 1. So 2 as sure. Yeah. It just loops forever. And like, stop. What are you doing? Okay. Yes, from all available evidence, they say. Yeah, I mean, it does in the example. Sure. Does it always get closer to skull? Sometimes the list may contain neither caps. Right. That's correct. The list may be a tube. Yes, if we start looking in this, we may never stop. I think my example was simpler. 7, go to 3, and you just so we start 1. It's a 7 element list, so we go to 7. We go to 1. Yeah. No answer. This is strange. Like, yes, it is strange. What happens? Functions like looking are called partial functions. What do you think the functions we have seen so far are called? Total functions. Can you define a shorter function that does not reach its goal? Maybe I'm going to test my silence removal. Well, I want to see if this chunk came out okay and then test my silence removal software. Okay. I'm trying OBS because recording the so I'm making these recordings and I want to finish them off in Descript. The reason being that even though I'm using some other silence removal software for reasons I'll explain very shortly, the transcript based audio stuff, like the way that Descript works is it looks for gaps between words. So if you're making a recording over a long period of time, you find you get like random noise and stuff. And there's some ways to deal with that, like setting a minimum length interval. But Descript, since it looks for words and you can shorten gaps between words, that does a good job of kicking out like all the random noises, regardless of if they persist for a little bit or not. So that's useful, because there will be random noises or like coughing or weird neighbor noises or car alarm or whatever it is, you know. But the thing about using Descript, I like it where I find it kind of annoying to have to like stop the video and start it again and have a bunch of separate recordings. So I like to keep it going for a while. And they do, the way that their system works is that it's the silence removal. It's like, they don't even call it silence removal. Like I said, it's like word gap space removal. So you need to make the transcript in order to use that feature. And so their service is keyed to having a certain number of hours per account level per month. And the amount of total video that you upload for transcription is the basis for those calculations. And it's not a huge amount of hours that you get. So like, you know, you could, if you like took a lot of pauses or you're thinking a lot, you could upload like a 4-hour video, but then it gets edited down to like 30 minutes after you remove the word gaps. So that's not really great. So what I'm gonna try is, and I discovered this software, it's like called Unsilence. It's command line software, and it removes silence from videos. But it leaves in like I haven't played with the settings a lot, but it like leaves in some stuff if it's, you know, I guess if it's a more persistent sound. I could probably play it, now that I'm thinking about it, I could probably play with the settings more and get it to remove more of that. But what I'm thinking is that I'll make the recording and then do a rough cut silence removal with the command line program that runs in Python, and then put it in Descript for like the final cleanup. That's what I'm going to try. So we'll see how that goes. And that'll also, it's, I don't know if I actually said that explicitly, but since I'll be doing the rough cut removal of the silence before putting it into Descript, that'll really save the amount of hours that get used. Now it does unfortunately like re-render the video because I don't know if there's a good way to not do that. So there is kind of a delay, like the Python unsilence removal program. So it takes a long time to run is the upshot there, but it addresses a potential bottleneck because like even on the higher tier plan for Descript, you only get 30 hours a month. And, you know, that's not bad if most of the stuff that you're feeding it, if you're feeding it mostly like content and not dead time. But if you're feeding it a lot of dead time, then you just burn through that really fast. And it'd be nice if there's actually like an upvoted feature request to run some sort of silence removal before the upload, because I'm not the only one, I think, who has that issue, although I think the specifics of the issues that other people have are a little different because they're like mixing multiple tracks and stuff like that. Whereas these videos, you know, they're pretty simple. But it's an issue of some kind for other people, but they just haven't gotten around to it, which sucks. But, you know, it's still a pretty good app, so I can't complain too much. Okay, so that was a little video editing tangent. So now let's go back to Programming Town. Oh, and just to finish off the tangent, the reason I'm trying OBS is because like QuickTime is really limited. Like you can make videos in it. It's really limited. The files it makes are pretty big. There's not much in the way of settings. It's just like I'm gonna output your whole screen at full resolution, haha. And that's a little irritating. And ScreenFlow is really buggy, really buggy. I found like the App Store review page for it, and it's got like under a 3 score, like a 2.8. And there's a whole bunch of complaints of it crashing, which has been my experience too. Which sucks because it's kind of an expensive app too. But like I'm not trying to make these. It can also be a bit of a heavier weight app than I really need. Like I'm not, because it's almost more of a video editor. And I just need something that has some customizable recording options, but that just will let me video the screen and work reliably and stably. So for that purpose, and it doesn't cost an arm and a leg, is the other thing. And for that purpose, OBS, which is free, seemed at least worth a try. So we'll see how that goes. I did have some initial issues with getting it set up. Minor stuff, just like I had doubling audio and that sort of thing. But I think I got that all squared away. So, yeah. Okay. So, where was I? We'll open up 9th chapter. There we go. So I'd rewritten it with their version, which is very exciting. And, oh, that's too far. Right, so Soren was simpler number. Let me get my blocking out the answers filter. I mean, it works. What is unusual about keep looking? Okay, I'd answered that before. Forget what their answer was. I remember answering that a few different ways too. What is unusual about keep looking? Let's just see. It does not recur. Okay, yeah. There's no could or lat. That is weird. Call this unnatural recursion. Okay. It's truly unnatural. Okay. Does keep looking appear to get closer to its goal? Yes, eventually. I mean, yeah, it appears to, but not every step is necessarily closer. Sometimes the list may contain neither caviar nor grits. That's for does it always get closer to its goal? Oh, right. So yeah, we did the looping. Yeah. I remember this now. Okay. You define a shorter function that does not reach its goal for some of its arguments. I don't know what they have in mind. I'm just gonna, yeah. Oh, I don't know that I would have guessed that. Eternity. Well, what's the goal? I'm not getting this. Oh, wait. Oh, that's a strange procedure. It just, so define eternity as an argument, as a function of one argument, x, and it invokes x, so it just keeps invoking itself endlessly. That's kind of weird. For how many of its arguments does eternity reach its goal? I would think none. And this is the most unnatural recursion possible. Interesting. Is eternity partial? Okay, so it was functions like looking are called partial functions. But if eternity reaches, I mean, I'd assume that it's called partial because it doesn't reach its goal or whatever for some arguments. But if something doesn't reach its goal for any arguments, it seems like it wouldn't be partial. Oh, they say it's the most partial function. Okay. What is shift x where x is ABC? I don't know. What does shift do? Does it move the first argument to the right or what? It'd be C, AB? I don't know. Oh, it moves the sublist brackets. That's interesting. Oh, I don't know, because that's scrolling in it, or is it A sublist B, C, D? Or A sublist B, C, and then sublist D? Or does it loop around? So then it's like sublist B, C, sublist D, A somehow? Or is it, yeah, I don't know. Oh, so it just moves the first sublist grouping one to the right. That's all it does. And it doesn't care if it's colliding with another sublist. Okay, define shift. Sure. So by the way, they say it's trivial. It's not even recursive. I don't understand why it wouldn't be recursive unless we're going to assume that the first value is always, like there's always going to be a sublist as the first element. I guess if you assume that. All right. I used build from a previous chapter because I wanted to do that instead of the two consing. So since they said it wasn't recursive, I figured maybe they were just making assumptions about the input. So let's see. Yeah, it looks like we're making assumptions. And they actually used they used build, but they also used first and second. Whereas I just used car and cutter. So describe what shift does. Shift moves the list grouping one over to the right. Here are our words. The function shift. I just wanted to put some of that in my Ulysses file. So the function shift takes a pair whose first component is a pair and builds a pair by shifting the second part of the first component into the second component. So the function shift takes a pair whose first component is a pair and builds a pair by shifting the second part of the first component into the second component. So a pair is a list with only two S expressions per an earlier definition of theirs, which is why, because I think this example is easier to see why this is a pair, but this example is a little less clear. But it has two S expressions. It's got the list and it's got the atom, so that's also a pair. Now look at this function, align. What does it have in common with keep looking? Not sure. Both functions change their arguments for their recursive uses, but in neither case is the change guaranteed to get us closer to the goal. Why are we not guaranteed that align makes progress? Well, let's think about this. So we've got some argument pora. First we check whether pora is an atom. If so, we return it. Then we check if it's a pair, or if the first element of pora is a pair. If it is, we shift it for some reason. Or, I'm sorry, we recursively call align. Imagine how this works. Right, so if we give it like our previous, something like our previous argument, sublist AB and then C, it checks if the whole list is an atom, and it's not. So then it checks if the first element of the list is a pair, and it is. Pora must be pair or atom. So if the first element of pora is a pair, can we trace a line? Define. Okay. So what was I saying? So for this input, the first argument isn't an atom. It is a pair. So then we recursively call myalign with shift, and then we check whether this is an atom again, and it is. So then we return this, and so that's, we just give it. So it's to the extent we want to give the procedure a goal, it's, which you could call the base case. I guess that's maybe what they kind of mean by goal. It's to find an atom. Oh, be careful not to call the original procedure when I, okay. So you see if you give it something like, we've got this nested structure. I guess this is still a pair because there's two S expressions. There's this AB list and C. But this first element isn't a pair, it's a nested expression. So it checks whether it's an atom, it's not. It checks whether it's a pair, it's not, meaning AB, nested list AB. So then it says, okay, well, I'm going to call build on that, and then call myalign on the second part, and then see if that's an atom. And it finds that it is, and it returns the whole expression. Or if it finds that it's a pair, it returns the whole expression, meaning the second element. So if you give it a non-pair, then it complains that it was expecting a pair because of a pair test. But I'm not sure what they have in mind by not making progress, other than just giving it an invalid, like a argument outside the program's domain. Okay. So they say in the second con line, so this one, shift creates an argument for a line that is not part of the original argument. That's true. Which commandment does that violate? The seventh commandment. Recur on the subparts that are of the same nature, on the sublist of a list, on the subexpressions of an arithmetic expression. So since we're making a new argument, that's a violation of it, I guess. It's not a subpart. It's a new argument at least smaller than the original one. It does not look that way. It can be like the same size. The function shift only rearranges the pair it gets. Yeah, that's true. That makes sense. That's what it does. And, well, if you're just rearranging the elements, you're not making it smaller. Both the result and the argument of shift have the same number of atoms. That's true. Can you write a function that counts the number of atoms in a line's arguments? I counter EV. That's interesting. Okay, so I'm having trouble with this for some reason, so I'm just gonna look at what they did, or at least at the start of it. Okay, I actually guessed that correctly. Stuck on this part. Con atom pora 1 else. Okay, is it gonna be? I'm not sure. So I thought of this. I was saying, well, maybe it's like length, add length car, length cutter. But then we get to the empty list and we have nothing to handle that, and we get an error. Oh, okay. So the book asks, is a line a partial function? And it says, we don't know yet. There may be arguments for which it keeps aligning things. Is there something else that changes about the arguments to align in its recursive uses? Yes, there is. The first component of a pair becomes simpler, though the second component becomes more complex. In what way is the first component simpler? Well, it becomes an atom from a pair. It is only a part of the original pair's first component. It's a little unclear. Doesn't this mean that length is the wrong function for determining the length of the argument? Can you find a better function? I'm not sure I understand. Oh, wait, what? Yeah, so they're making some assumptions here I'm not quite following, but I'll switch to read along mode until it starts to gel, hopefully. Like, keep looking, eventually dead. How much more attention should we pay to the first component? At least twice as much. Still not really following this. So weight is just multiplying the value of the first part of the pora for some reason that I'm not quite sure I understand. I accidentally saw the answer here, but what is weight x when x is ABC? Wait, was it 7? Trace my weight. Oh, I see. So the way this works, it's going to so the initial value is sublist AB and C, and it says, okay, well this is an atom, so for the first pora, which is the list AB, multiply whatever that is by 2, and then it says, and then it recursively calls weight, which says, okay, well now we have this list AB, so for the first value of it, which is A, multiply whatever that is by 2, and so then it analyzes A and says, okay, well, A is an atom, so we return 1. And then, so it multiplies that A by 2, because it's the first element of AB. And then it adds that to B, so you get 3. And then it multiplies that 3 again by 2, as the list AB is the first element of the entire argument. And so then we get 6, and then we just add the 1 value from C to the 6, and we get 7. I think it would be 5 for this question, because the A would get times 2 for being the first element of the whole thing, and then that's all the bonus it would get. That's all the extra weight. And then within the list, the B would get times 2 weight as the first element of the list, but the list wouldn't get a bonus, so we would just get 3 from the list and then 2 from the A, so 5. Let's see. Now I could just see what the book says, but I like tracing things out. Oh, I accidentally nested it. Okay. Okay, 5. We got it. We're killing it. Does this mean that the arguments get simpler? I don't know what they mean by that. Yes, the weights of a line's arguments become successively smaller. This chapter needs a companion video. Is a line a partial function? No, it yields a value for every argument. Alright, I figure I can at least found this pretty recent, only last year. Sometimes the stuff that you find for these books is like, it's like from a decade or 2 ago. But Bro talks about this chapter a little bit, and he has some links. So I'm going to read some of these. Maybe I get some more value out of this chapter. As a good programmer, do you use functions? I'll probably give you a funny look. Of course I use functions. I use a function, tell me what time it is, save data to a database, blah, blah. Use functions all the time. If a mathematician happened to be within earshot during the conversation, she'll probably give him a funny look. None of those things are functions. She'll point out a function is a mapping from a set of inputs to a set of outputs. They have two fields have 2 different definitions of functions. Perhaps because I'm a fan of descriptivism, I'm not interested in trying to argue that one of them is right and the other person is wrong. Instead, I'll point out that because of this ambiguity, we humans have come up with the term pure function and impure function to disambiguate which function we mean. A pure function is a function in the mathematician's sense, a mapping from a set of inputs to a set of outputs. The output of a pure function is determined completely by its inputs. If you pass value 3 to a pure function and it returns 15, then by virtue of the fact that the function is pure, you're guaranteed that anytime you invoke the function with 3 again in the future, it will always return 15. This is in contrast to a function whose output may depend on the current time, or a function which reads from a global variable as part of how it determines its output. Passing in the same inputs might yield a different output for two different invocations. A pure function, by definition, does not have any side effects. So not only are we guaranteed that a pure function will always return the same output given the same input, but we're also guaranteed that the function will do nothing except return its output. This is in contrast to a function which writes something to disk, sets a global variable, throws an exception, or anything else besides returning a value that is in some way observable to the caller. It is always safe to replace a given invocation of a pure function with the result of that invocation. For example, given the code snippet x equals f of 1 plus f of 1, if you know that f is a pure function, then it is safe to refactor this code to x equals 2 times f minus 1. On the other hand, if f was impure, then this refactoring might have introduced a bug. For example, perhaps f incremented a counter and the original implementation would increment the counter twice, whereas the refactored implementation will only increment the counter once. Okay, that makes sense. So you're only calling it once. Incidentally, a bit of jargon for you, we refer to the concept. It is always safe to replace a given invocation of a pure function with the result of that invocation as referential transparency. Okay. Pure functions are easy to test. One nice property of pure functions is that they are much easier to test than impure functions. A pure function simply returns some result given an input and is guaranteed to do nothing else but return that result. Therefore, to test a pure function, you only need to provide it an input and then check that the return result is what you expected it to be. You're testing a function for which its output depended. I don't like the for which here. I prefer whose, even though it's kind of personalizing the function. You're testing a function whose output, for which its output is kind of awkward. Whose output depended on something other than the parameters you pass to it, then you'd first have to know what those hidden dependencies were. Yeah, that makes sense. Which would possibly lead to your test becoming coupled to the implementation of the function instead of its contract. And then you need to see if you can intercept and control those hidden dependencies somehow. If you're testing a function which produces a side effect, you often don't want the side effect to actually happen during testing. Let's say you have a function delete user from database that you want to test. You want to check that the function is capable of deleting users, but you definitely don't want your test to connect to the real production database. What if there's a bug in implementation and it deletes the wrong user? I mean, you're testing this function because you're not sure that it's bug-free, right? In practice, this usually means creating one or more mock objects. But this assumes that the function under test provides some sort of hook so that you can inject in your mocks. If the function is hard-coded to connect to a database, and interjecting your mocks may be difficult or impossible depending on what programming language you're using and what facilities it provides. If you're testing a function which does not. Okay, let's go down to the total functions part. Related term is total function. Function is total if it's defined for all of its possible inputs. As a counterexample, consider the function tail that takes a list as its input and returns a new list which is equal to the original list except with the first element removed. Tail is not a total function, it is a partial function because it is not defined for the empty list. Okay, that makes sense. Note that total and pure are orthogonal concepts. A function can be both, neither, or any combination in between. Not x boolean, which returns the negation of its input, is both pure and total. If a partial function expresses its non-totality via mechanisms such as throwing an exception, then the caller can usually observe the fact that an exception was thrown via a catch, for example, via a catch statement. How long is this? Now we're almost there. In such a case, we would say that the partial function is impure because it triggered an observable side effect. On the other hand, if a partial function expressed its non-totality by not returning, by going into an infinite loop, then the caller would never have the opportunity to observe any side effect. Hence, the function is pure. Notice that if you're working in a programming language which allows you to throw exceptions, but provides no facility to catch exceptions, then from the caller's perspective, this is the same as the infinite loop example. The caller has no opportunity to observe any side effect, and thus the non-total function is also pure. Basically, pure functions return the same output given the same input, and total functions are defined for all possible inputs. Okay. I realize it's probably better to call these dialogues than exercises because they're not really normal exercises, so I'll just call them that. Yeah, I'm not going to worry about the previous stuff though. I'll make sure I put a link to this article at some point. Comments are closed. Why you close comment? I hate when people do that. Okay, I have to remember to always test Descript. Even if I just take a break and come back later for more in a session, because when I was initially trying to record stuff, I remember to I took a break and then I came back and I was going to start another video, but then I figured, well, let me just test again to make sure, and the audio wasn't working and I had to restart Descript for it to work. So okie dokie. Right, so now they want us to do insert R. They want us to use their insert G to make insert R. So it's going to be pretty straightforward. Insert L, that's why. Okay, so yeah. Well, now we have the comparison. Yeah, with insert L, we insert the 0 to the left of 3, and with my new insert R, we insert the 0 to the right of 3. So that's working. Yeah, pretty straightforward stuff. Is there something unusual about these two definitions? Well, I just saw that they said yes, but I didn't see the reason. Oh, let me copy paste that. Okay. Well, in terms of the stuff that we've been doing so far in the book, mostly we've had lambdas, but such that I even initially, as I think I mentioned earlier, tried to put a lambda in one of these definitions, but since they return a function that takes arguments, since for whatever argument we give their insert G or insert G, as we've defined it, we return a function that takes arguments, then we don't need a lambda. I guess the other thing is, we've used non-primitives to define procedures. But yeah, just that whole method of using a function, creating function in order to define arbitrary functions in terms of that function is like a new thing. So this is more like the big picture thing, and this is sort of like the more mundane point that's related to the big picture concept thing. Okay, it seems like they might have a slightly different point in mind. Let's see. Earlier we would probably have written define insert L, insert G sequence, where sequence is sequence L, and define insert R, insert G, but using where is unnecessary when you pass functions as arguments. Oh, are they just talking about like how they would write or describe it? Because yeah, they generally do that thing where it's like, if one of the arguments is the formal parameter for it is A, and in the specific example it's potato, they'll say like, what's the value returned for this argument, for this procedure when for argument A where A is potato. Okay. Is it necessary to give names to sequel and sequar? No, you could just call insert G with a CQL and then pass arguments to that. Not really. We could have passed their definitions instead. Okay. Define insert L again with insert G. Do not pass in SEQL this time. Yeah, so we can just do the lambda directly. Yeah. Okay. So we'll be continuing with Little Schemer Chapter 9 after a little break. I'm still not quite sure I understand the whole weight thing, like the purpose of it. Like I understand how it works. It's not very complicated. I do like to understand the purpose of it as I go about dealing with them. But I'll just keep pressing on and maybe it'll become clearer, maybe not. So there's some respect they're saying in which the arguments become simpler, the arguments to align, because by virtue of the shifting that occurs where we move values, or we move the grouping, I should say, rightward within the argument. Like we take the argument and we move the A out of the list and group, or actually, let me try to be more precise. So they actually, how did they put it? The function shift takes a pair whose first component is a pair and builds a pair by shifting the second part of the first component into the second component. Yeah, so it does that, but it also, by consequence of that, it leaves the first component alone as an atom, as a not list. I mean, it's still within the greater list, but it's not a list within the first element is not a list within the list that constitutes the whole argument anymore. It's just A instead of A within the list AB. So they're saying basically we can define this weight function and we can see that by virtue of the shifting process, the weight is reduced, which we can say is a criteria by which we can judge the argument as, or the value of the successive arguments that result from invoking shift on an initial argument that is a valid argument to align, that they're becoming simpler in some way because this value is going down. And this simplicity, I guess, is this increased simplicity is a less obvious but analogous to the increase in simplicity that you get when you recurse through just a list of atoms, a list of words, and you take off the first word each time until you get to the empty list. And this is, I think, meant to be just another type of that same increased simplicity, I think. So here's shuffle, which is like align but uses rev pair from chapter 7 instead of shift. Okay. The function shuffle and rev pair swap the components of pairs when the first component is a pair. Let's see how that, assume it's already, or actually you should use the interactive window. A, B, C, D. Yeah, that was weird. Nothing happened. Let's try defining it. Find shuffle A, pora, else build. I mean, shuffle is total. We don't know. So for shuffle this value, we get the same thing back. I'm thinking it's not total because this seems to have, oh, I should run trace. Totally a partial function. We outed it. Very weak, partial, incomplete function. Very sad. Okay. It's enough mocking the function, Justin. Okay, so why isn't it ACB? So, okay. This whole thing is passed as an argument. It's not an atom. The first element is not a pair. So then it goes to else. So then it says build first pora, which is going to be A. And that's going to get const onto the result of invoking shuffle with the second. Just make sure I'm making like a, yeah, okay. It's going to be BC. That's what I expected. BC is not an atom. Oh, yeah, I was making a basic mistake. Because I was thinking I was going to check whether this, whether BC was a pair, but it's going to check whether B is a pair, which is not. That's why. That's why it doesn't reverse it. Okay, that's fine. So, if you give it, say, sublists A, B, C, D, I'm sorry, um, yeah, that sublist AB, sublist CD as this argument, then what happens? Well, it checks whether this whole thing is an atom, and it's not. So then it checks whether this is a pair, and it is. So then it reverses. It calls reverse pair on AB, sublist CD, and then it invokes shuffle with that as the argument. And then it checks whether that whole thing is an atom, and it's not. And then it checks whether it's a pair, and it is. So then it invokes rev pair on that and passes that again as the argument to shuffle. And so you see the problem. A, B, C, D, it will loop endlessly because it will keep reversing the order of the pairs and invoking shuffle on them. Okay, that's true. Shuffle X where X is AB. So, not an atom. It is a pair. Oh, but wait. Gotta be careful, right? This first is going to be A. So it's not a pair. A is not a pair. AB is a pair, but A is not a pair. So we would go to the else, build A, invoke shuffle on B, basically, which is an atom. So when we return the atom, then basically we're going to cons the A onto the cons of B in an empty list, which is going to get us the same list we started with. Yeah, it's a sort of elaborate indirect way to get the same thing you started with. Yeah, they do the exact example that I. So they say for shuffle X where X is ABCD, they need to find out what shuffle rev pair pora is where pora is ABCD. Figure that out. They're going to determine the value of shuffle pora where shuffle pora is where pora is CDAB. Doesn't this mean we need to know the value of shuffle rev pair pora where rev pair pora is ABCD? Yes, we do. And the function shuffle is not total because it now swaps the components of the pair again, which means we start all over. The function total is this function total. Oh, it's a new function. Find C. So if n is 1, it returns 1. Otherwise, it loops with 0. So if n is 1, return 1. If n is even, divide n by 2 and invoke C again with that. Otherwise, multiply n by 3 and add 1. Cond 1n, 1 else, cond even n, C else, C, add 1. Oops. Oh, I see what I did. So we can see it working some. Start out with 5. That's not 1 or even, so we do the multiplication and then add one thing. Then that is even, so we divide it by 2. Yeah, basically it gets down to 1. It doesn't handle negative numbers. And 0, it just loops. Okay. This function total, well, it seems not total. Doesn't yield a value for 0, but otherwise nobody knows. Okay, so it's a mathy thing. That's cool. What is the value of A10? Well, what is A? 2. Okay. A11, 3. A22, 7. Huh. Alright, so what pattern is this? I wonder. Let's just see the function. Here's the definition of A. Lambda n m con 0n add 1m. If 0, if n is 0, add 1 to m. If m is 0, recursively invoke sub 1n. Recursively invoke A with 1 less of n and the number 1. So, what does A have in common with shuffle and looking? These arguments, like shuffles and lookings, do not necessarily decrease for the recursion. How about an example? So you see that actually goes up. Oh no, sorry, that's my C. Fine. Used to loop when you give it 3, 3, so I think it's another partial function. Say, how about an example? That's easy. A12 needs the value A0, A11, and that means we need the value of A03. Wait, is it? Maybe I just didn't let it run long enough. I guess there's just a lot of intermediate steps, but yeah. Okay. The trace result fooled me as to whether it's gonna terminate. So then they say, then what is A43? For all practical purposes, there is no answer. Okay. What does that mean? The page you are reading now will have decayed long before we could possibly have calculated the value of A43. Okay, that's a little meta book. Wouldn't it be great if we could write a function that tells us whether some function returns a value for every argument? Sure, that sounds pretty cool. It sure would. Now that we have seen functions that never return a value or return a value so late that it is too late, we should have some tool like this around. Okay, let's write it. It sounds complicated. A function can work for many different arguments. Let's make it simpler. For a warm-up exercise, let's focus on a function that checks whether some function stops for just the empty list, the simplest of all arguments. That would simplify it a lot. Now that's interesting because they give you a starter. How would you? So we'd want to pass f the empty list, but then what do we want to do to that? You know, what does it do? Does will stop return a value for all arguments? That's the easy part. We said that it either returns true or false depending on whether the argument stops when applied to the empty list. Will stop total then? Yes, it is. It always returns true or false. Let's make up some example. F is length. You know that length L is 0 where L is the empty list. So will stop should be true. Will stop length should be true. Absolutely. How about another example? What is the value of will stop eternity? False. Eternity quote doesn't return a value. We just saw that. Does this mean the value of will stop eternity is false? Yes, it does. Okay. We need more examples. Perhaps we should do one more example. Last try. Procedure. Function of one argument. Wait, what? So last try. So will stop would give last try the empty list, which last try would pass to eternity. Last try would return true if will stop last try and eternity x were both true. But eternity x is not going to return anything. And will stop last try is just going to trigger another invocation of eternity x, of eternity with the empty list being passed. I think will stop last try should be false, but I'm not sure. You need to test it on the empty list. If we want the value of last try quote in the list, we need to determine the value of and will stop last try eternity quote. What is the value? Right. So they're saying, right, if we want to determine the value of last try with the empty list passed to it, we need to determine the value of this. But to determine the value of that depends on the value in part of will stop last try. And the value of that is going to depend on last try with the empty list. So we just go in a circle. There are only two possibilities. Let's say will stop last try is false. Okay. And false eternity quote and false, which were stipulated, along with eternity quote or eternity with the empty list is false, since and false is always false. That makes sense. So last try quote or last try with the empty list stopped, right? Yes, it did. But didn't will stop predict just the opposite? This is tricky. Oh, so we stipulated that will stop last try was false, and then we analyzed that. Okay, we stipulated that will stop last try was false, the meaning of which is that last try won't stop. But when we analyze that, we wound up with the result that last try did stop. So we must have been wrong about will stop last try. That's correct. It must return true because will stop always gives an answer. We said it was total. Fine. If will stop last try is true, what is the value of last try quote? Last try empty list. Yeah, I don't know. Now we just need to determine the value of and true eternity and then empty list. Eternity invoked with the empty list, which is the same as the value of eternity invoked with the empty list. What is the value of eternity empty list? It doesn't have a value. We know that it doesn't stop. But this means we're wrong again. The book is messing with me. True, since this time we said that will stop last try was true. So we're contradicting ourselves. We're going in circles. What do you think this means? Here's our meaning. We took a really close look at two possible cases. If we can define will stop, then will stop last try must yield either true or false. But it cannot due to the very definition of what will stop is supposed to do. This must mean that will stop cannot be defined. Okay, so we can't figure it out. Is this unique? It makes will stop the first function that we can describe precisely, but cannot define in our language. Is there any way around this problem? No. What is define? We just saw that is an interesting question. We just saw that define doesn't work for will stop. The previous chapters are much more conventional than this. This is turning into a brain bender. So what are recursive definitions? It's like getting a little philosophical. Hold tight, take a deep breath, and plunge forward when you're ready. Okay. Is this the function length? That looks right. Sure is. What if we didn't have define anymore? Could we still define length? Without define, nothing, and especially not the body of length, could refer to length. Okay. What does this function do? It returns a procedure. Wait. Returns a procedure which, if the list is empty, returns 0, and otherwise adds 1 to the result of calling eternity on the remainder on the cdr of the list. It determines the length of the empty list and nothing else. Yeah, I guess. Yeah, I was like, initially I was like, oh, this looks kind of, oh, eternity, I see. And then it's not defined, so. What happens when you use it on a non-empty list? We don't get a result, I'm guessing. No answer. If we give an eternity an argument, it gives no answer. That's right. Right, because eternity just invokes itself on the argument. You give it eternity 1, it says, okay, eternity 1, eternity 1, eternity 1, forever. So it just won't give any answer for non-empty lists. Suppose we could name this new function. What would be a good name? Length 0, because the function can only determine the length of the empty list. Not a very useful function. How would you write a function that determines the length of lists that contain 1 or fewer items? You could do like, because there's like a 1 question mark primitive. So you could do 1L, 1, null L, else null L 0. Or I should say, I should have written it out. You would need to do null L 0. If you know it's 1 or 0, you could just test one case, and then if it's not, just else return the other. But what do they do? Well, we could try the following. This seems more complicated than you would need, but I don't know. Yeah, I see. Right, so you see that it's like building on length 0. Call length 0 with the empty list, you get the 0, and then you add 1 to it. You say almost, but define doesn't work for length 0. Doesn't it work for length 0? Seems to be definable to me. I don't know, man. Oh, okay. So my parentheses, but I got this to work. That's a good name for this function. That's easy. Length less than or equal to 1. Yeah, I must be missing something because I'm like, well, if you just want to address these two cases, why don't you just do con, null, L0? And if you want to look for those specific cases as opposed to doing alternative, you could just be like, well, actually, let me think about that. So we're trying to define length. But yeah, but I'm thinking about a different angle. I'm not sure why they said you can't define, why define doesn't work for length 0. Like that confused, because it seems to. And then they ask, is this a function that would determine the length of lists that contain 2 or fewer lists? And so we're just building up like a stack of these. Null 0, else add 1. Yes, this is length less than or equal to 2. We just replace eternity with the next version of length. Now, what do you think recursion is? What do you mean? Well, we have seen how to determine the length of a list with no items, with no more than 1 item, with no more than 2 items, and so on. How could we get the function length back? If we could write an infinite function in the style of length 0, length less than or equal to 1, length less than or equal to 2, then we could write length infinity, which would determine the length of all lists that we can make. How long are the lists that we can make? Well, a list is either empty or it contains 1 element or 2 elements. Yeah, there's no limit. But we can't write an infinite function. No, we can't. So we give up. Say the book is stupid for suggesting the idea. No, I'm sure they have a solution. And we still have all these repetitions and patterns in these functions. Yes, we do. What do these patterns look like? All these programs contain a function that looks like length. Perhaps we should abstract out this function. Let's do it. We need a function that looks just like length, but starts with lambda length. What's eternity? What role is that playing here? Oh, okay, duh. Okay, I got it. Right. It was just a matter of seeing where the so this returns a procedure. The part that I've highlighted and pasted it into the Racket to get a better picture of it. But the part that I've highlighted returns a procedure, which then takes an argument. And if you pass eternity in as the argument, it goes here. So then it's the same as length 0. Still a little shaky, so I'm going to see how they do length 1, and then maybe I'll try length 2. So the bottom part returns an argument which is like length 0, and then it gets returned as basically the f argument to the top lambda, which itself returns an argument which then you could invoke on something that's on a list that's 1 or 0 atoms long, call it. One stray parentheses is just chaos. Yep. Okay. I'm just testing my stack of lambdas to make sure it handles the cases that it's supposed to. So they use length instead of F, G, H, but it looks basically the same. Yeah, looks fine. They say, so they want to get rid of the repetitions, and they say, name the function that takes length as an argument and that returns a function that looks like a length. But we have a couple of, well, let's see what they say about make length. Now, when they say do this to length 0, like, do we want the function, do we want make length? They say name the function that takes length as an argument and returns a function that looks like length. So we want to return a function. So I think we have 2 lambdas, like we did in our previous stuff. But I think, and then do we want to pass eternity in to make length as the argument, or do we want to do that? I think it has to be this way, because the other way, we're not making a length function, we're just defining eternity. We're defining length 0. I don't know though. Yeah, okay. I mean, I find this structure a bit weird. So, yeah, so I find this way of writing it weird, because like I think of this as the argument to the function. Now, of course, the argument can be a function, but I'm just like, well, why wouldn't you just use define? So like this lambda returns the length procedure or length 0 procedure, or I guess it returns a function that could be customized as the length 0 procedure. Right, it's the make length procedure, which then is taken as an argument, make length, and then this procedure is invoked on eternity. So eternity goes into the body of this procedure and is substituted in for length, which is the argument. Then it becomes, you see, eternity goes here, and then it becomes length 0. I'll write it their way because I find lambdas tricky, so it's good to practice. They say, is this length 0, 1? Right, so we've got the make length procedure again, and it returns that procedure, which is then invoked with make length eternity, which is the length 0 version of the procedure. And then that procedure is passed in and becomes the, so length 0 then becomes the argument to make length, which is similar to what we saw earlier, where we had the make 0 lambda, and then that went where, let me see if I have like that length, and this lambda, it's the same thing, essentially. It sure is, and this is length 2. Right. Okay. I think I'm following this, actually, somewhat to my surprise. Oh. Actually, I needed one more. Okay. Yeah. Make length eternity 0. So to get to 3, we need 4 make length invocations, including the base invocation. What is recursion like? It is like an infinite tower of applications of make length to an arbitrary function. Do we really need an infinite tower? Well, if we want to be able to handle things of arbitrary length. Not really, of course. Every time, okay, yeah, I see what they're saying. Every time we use length, we only need a finite number, but we never know how many. Could we guess how many we need? Sure, but we may not guess a large enough number. When do we find out that we didn't guess a large enough number? Well, when the program doesn't return anything. When we apply the function eternity that is passed to the innermost make length. If we could create another app, wait, let's back up. Okay, so I think we're about here. So, well, since nobody cares what function we pass to mk length, we could pass it to mk length initially. Okay, there's a leap being made here. So before we were passing eternity as sort of the base case of the tower of, it's not really right to call it the base case, but as the initial function to, or initial function that we passed in as the argument to this like tower of procedures. But now they're saying you could just pass make length itself. I'm a little confused. If we use a name like make length, it is a constant reminder that the first argument to make length is length. Okay. I'm trying to figure out how to think about this. So this version from earlier was like, or actually let's find a simpler version. So this procedure takes the eternity function as an argument and returns a procedure with that performs this, returns a procedure that does this, but with eternity substituted in here into the body. And then you can invoke that procedure. You could give that procedure an argument, which would be the empty list, and get that the list is length 0. And then this returns a procedure where this, instead of eternity being the argument function, make length eternity is like the argument function to this. And so then make length eternity is the thing that winds up being substituted. So then you can, and with that, you can calculate up to length 1, and then so on with length 2 and length 3. But it's okay. This I find trickier to follow. I mean, I even found that tricky to follow, but now this is like another step of trickiness. Lots of Stack Overflows for the little schemer. Okay, so we got a few. So let me see if I can follow this guy's question. The little schemer, there we go. The little schemer gives the following on page 165 as function length 0, as still the function length 0. But how does this work? It looks like the length lambda is being passed. So by length lambda, I think he means, oops, grabbed the wrong one. This is the length lambda is being passed to the make length lambda, which would be this. Oh, my circling was a little sucky there. I think you get the idea. Which evaluates the length lambda with the length lambda itself passed as an argument. So then when length L at the bottom is evaluated, length is just the length lambda itself. But the length lambda takes 2 parameters curried, length and L. So there's 3 lambdas. So I'm not quite sure I follow this guy's question, but and I see what he's saying these are curried. I'm gonna try reading the responses. Little schemer is building up I'm gonna skip over this for now. Little schemer is building up a function that will work for lists of greater and greater length. Part of the point of length 0 is that it only works for lists whose length is less than or equal to 0. And since there are no lists of negative length, that means lists of length 0. The code that you've shown intentionally works only for lists of length 0. Yeah, that's true. I follow that. This isn't really, I feel like this isn't really directly responding to the question. Like he seems to be asking, oh, so now I'm reading this comment. This person says, correct, it doesn't. So this is a reply to, you gotta figure out like what the reply is mapping to in the original. So how can length could or L make sense because of all this? And this person says, correct, it doesn't. It returns to lambda L to add 1 and thus causes an error. That's why it's length 0. It only works for empty lists. And the name length is wrong too. And it really should be called make length as it is in the right half of that frame. Now let's look at these other. I spent a day reading page 166, length 1 in the book. A day is a long time to read this much code. That sounds like getting stuck. I get stuck too, but I get stuck on questions. Like I think I've mentioned this before. I'll see a question like at the end of a chapter, not in this book, but in another book, and there'll only be a few, and I won't want to waste it by looking at the answer. So then I'm like, I'll be stuck on it for a while. But if it's in like the body of it, of the text, and I don't quite get it, I'll try to get it, but then I'll be like, after a while, I'll be like, okay, well, maybe this will get clearer later. I don't know. I'll just kind of move on. It gets tricky though, because I don't want to say it's a balance, because balances tend to not hold up under scrutiny. But on the one hand, you don't want to have low standards for understanding and continue on when stuff is not making sense. But on the other hand, you don't want to like spend infinite time stuck on something that is maybe not even that important. And when you phrase it like that, then thinking of it as like a balance, that sounds plausible. But really, what you need to do is you need to figure out like what points are important, and then figure out some way to figure those out conceptually. But when you're learning a new area, it's hard because it's like because you don't know the area, so then maybe any given point could be important, and you don't have the judgment to know that. So you've just kind of got to make a guess as to like, well, this seems important and this seems not, and you might be mistaken about that because you're learning. And that's where people get in trouble, where they like try to do 100% completionist understanding, which could take forever and not be very effective, or just like the other side of the coin, which is just sort of half-assing it and then not being able to do stuff in the field. Anyway, this is a bit of a tangent, but I think tangents are good, at least somewhat. There's really an exponential jump at the end of this book. Like the first 7 chapters were a breeze, 8 starts to get hard, and then really hard towards the end, and then 9 is taking some time as well. So then if I get through 10, then it'll be like having a PhD in computer science, as if if this trend line holds up. Okay, let's try reading this again. So this is for make length less than or equal to 1. Okay, let me actually go through this. So this is this function, which they're saying is length less than or equal to 1, which that's what the book says. And this guy says, so he's invoking this. Notice there's an extra paren here. So he's invoking this on L, where L is apples. And he also specifies what eternity is, which is just the partial function that infinitely calls itself. So he says, page 166 states that when we apply make length once, we get length less than or equal to 1, which you can see over here. And then could we do this more than once? But I do not know how to do this for getting length less than or equal to 2. So someone says, suppose L is apples, then it'll evaluate like this. Notice that make length is bound to the typo, lambda make length function itself. So con nulls list 0. That's not true. Otherwise, make length, else add 1, make length eternity, cutter L. So the list is not null because it has 2 elements. So this condition fails. So then we go to the else. So we add 1 to the result of calling make length with the eternity function on the cutter of list, which in this case would be oranges. And you can see that's what he does. So add 1, make length eternity on oranges. So then that becomes add 1. So then this becomes add 1 to, so for list oranges, null is not going to be met again. So then we add 1 to or I should say, so then we go to else again within this procedure, which leads to another add 1. I'm trying to figure out the eternity thing. So we invoked make length with eternity. I get that. I'm trying to figure out why isn't it just like eternity is being evoked on the cutter as opposed to eternity and trinity? I'm a little confused. I was looking at an earlier structure of the procedure. Maybe I was confusing myself. So So in the little schema book, chapter 9, when building a length function for arbitrary long input, the following code is the following suggested. Make length. Okay, this is actually a bit ahead, so let me read ahead. Let me read a bit more. I see there's that and a very long explanation of what the chapter is getting at as well, like overall. So we'll read that too. So what is the value of make length? What, is that the same? Lambda make length L. No, that's a bit different. Where L is apples. So I guessed it'd be 1 because this returns a procedure. So I found this page, and the guy links to a PDF he made. Oh, look, he likes Feynman too. Okay. So it has some mathy looking stuff. I kind of skipped because I was hoping I could just follow the scheme part better. So the length as written in the little schema more or less looks like the following. Length lambda L con null. If L is null, return 0. Otherwise, add 1 to, well, that makes sense. However, a lambda version of length will look like this. Lambda L con null L, then return 0 else, add 1 to mystery could L. So as you can see, we have a blank to fill in. We don't know how we can call this function recursively because lambdas don't have names. However, above will work for lists with length 0. Right? That makes sense because it explicitly handles the 0 case. But if we notice we can pass in another function in place of blank, it will work for lists with length 1 as we can see below. Right? Because if we give it a list of length 1, we'll say, well, it's not null, so we go to the else, and then we add 1 to the, so this gets evaluated, returns could L. I'm sorry. Yeah. So this lambda evaluates the could of the 1 element list, this inner lambda. Right? No, that's terrible. Evaluates the could L of 1 element list, says, hey, that's null. So I'm going to return 0. And then the higher level lambda adds 1 to that. And so, yeah. Okay. So I'm following so far. But it will only work for lists with length 1. If we try it with lists of length 2, it will fail. It will fail because for the last element of the list, it will not yield another function when it's about to expire. However, following program will work for lists with length 2. So it's the same principle. If you give it list length 2, the inner lambda says, by the time it gets to the inner lambda, it's been cuttered a couple times, so it's null. It returns a 0. The lambda 1 level up returns 1. The lambda 1 level up returns 2, and then you're good. But he says, but this is not going to work. I think he means it's not going to scale up well. We will have to keep passing the functions, and it will be hard to guess in advance as to how many functions do we have to pass. So in order to make things work in a different way, we can pass in a function to this lambda expression. Goes here, length goes here. And above expression, the length on the right will be applied to the length on the right. Talk is cheap, so let's look at some code. Length on the right will be applied to the length on the right. Is that a typo? All right, so found a video. So I think because of how I set up my audio, the audio from the video won't go into my video. But me watching the video will just get edited out anyway automatically. But I've put the link to it in the blog page for this chapter. So this looked promising because he specifically mentions the little schemer and length. And he's doing, I guess it's Python, but hopefully he'll say something relevant. So this chapter is talking about Y Combinator, which I don't really know what that is yet. But the problem with searching for Y Combinator is that you get Y Combinator, you get the startup thing, and not the programming concept so much. So like if you go to YouTube and you search Y Combinator, even if you Y Combinator a little schemer, like this was like the one thing I found that was like, oh hey, this might actually be relevant to what I'm looking for. So the question he's starting out with is like, what if we didn't have def? Could we do recursion anyway? Okay, I found this other video. I seem to be able to find, I started finding more videos that are actually on topic. Oops, that's weird. And I might go back and watch his lambda calculus video too, because he refers to it. Guy's computer file. Maybe he gets a subscribe. Check out his new stuff. He started talking about recursion in terms of the Factorial program, and then he's talking about so he says this is the simplest recursive program he can think of, which is just it's a loop. It's just a program that calls itself, which is kind of like eternity, right? In the little schemer, because yeah, it just calls itself. Like you give it an argument and it just calls itself with that argument endlessly. So it's pretty similar. He's talking about the idea of self-application and applying a function to itself is how you can recurse using lambda in a language where you can't define things. So the second copy of loop or whatever is the argument to the first copy, and then when we do substitution, we just wind up where we started, where we have a couple copies of loop, I think is what he's saying. I found another resource. Following is the most distilled top-down explanation of the Y Combinator I could possibly come up with. That sounds promising. That still, according to my hopes, remains comprehensible. You might want to read this either as a warm-up before diving deeper, or after reading one or two more verbose tutorials with a bottom-up approach if the concept hasn't quite clicked yet. Code is enclosure, a list dialect. The only thing that should not be instantly comprehensible for Lispers is the following built-in macro. Foo percentage is an alternative syntax for denoting lambda, the same as fnx foo x. I'm not familiar with this notation either. Darn it. I'll use that form to denote these lambdas, those lambdas that are really just redundant wrappers, serving no other purpose than to delay the evaluation of their wrapped expression. Problem: we have an anonymous function f that we'd like to be able to call recursively without the means of explicit self-reference. Solution: the Y Combinator is a clever function that can create a modified version of f that is able to recurse without knowing its own name. I will first show the so-called strict version of the Y Combinator, commonly called the Z Combinator. The subtle difference will be addressed later as a preliminary step. We need to move the self-reference out from the function f. That is, the Z Combinator does not work on the original function, but expects a wrapped version of f, a maker for f if you like, that returns an f that calls the maker's argument, a bound variable in the enclosing scope that's perfectly okay at the point of recursion. Okay, I'm looking at one of his links now because I see that it's longer, but it's written in the notation style I'm more familiar with. So here's a simple recursive factorial function in Racket. Note the use of the slightly longer lambda notation. That's fine. Okay. So define fact, going to be procedure of one argument, n. If n is equal to 1, we return 1. Otherwise, we multiply n by the result of calling fact with n minus 1. Very straightforward. As natural as this might appear, this makes use of the ability of Racket to reference identifiers within their definitions, which of course is the heart of recursion as a programming technique. However, when we try to translate these recursive definitions into the lambda calculus, we run into some trouble. Because all function creation expressions use lambda, these functions are not named, so of course cannot be referenced within their bodies. And yet it is possible to express recursion in the lambda calculus without using self-referential identifiers. This is probably the most intricate technical topic presented in a course, so please do read the article slowly and make sure you run all the code examples as you progress. Okay, moving to self-reference. The problem with the above definition is the recursive reference to fact. Our first step will be, I think, to create a higher order function which fills in this function. Right, okay. So now we're defining a factorial maker, a factorial procedure maker program. We're not quite solving the problem yet because we're not defining it. We haven't figured out the problem of recursing without definitions yet. This is just an intermediate step. And they say, okay, So define fact maker lambda f. This is a body of fact except using the parameter f. Right. So when we pass in fact, the procedure into fact maker, it's got the body of fact. It's got the body of fact in there, except that where the self-reference was, now it's taking an argument. It's taking a procedure as an argument. Now it says, this doesn't solve the problem. In order to achieve the factorial behavior, we're still using the recursively defined fact. However, the above definition yields a very interesting observation. Fact maker fact is identical to fact. And I think what they mean is the higher order procedure fact maker that when passed the factorial procedure creates a complete factorial procedure. When it is given the fact as the argument, as an argument, the result is a procedure that functions identically to the normal factorial procedure. So in other words, the higher order procedure that takes factorial as an argument and substitutes it into the body of the higher order procedure, substitutes it into where there used to be in the original factorial procedure a self-reference, leads to a procedure with the same function. So I think where this is going is if you could have a lambda procedure that's a higher order procedure and that takes as an argument another procedure. I'm not saying this very precisely, but so understand that. But then you could use that same sort of pattern to get recursion without having to name things, I think is what this is building up to. Ooh. Okay. So in this version, they've replaced fact maker, or they've replaced the F, which used to stand for the self-reference, or okay. So initially we had the self-reference. Then we had this parameter f. And now we have an invocation of the fact maker procedure on parameter f. At this point, you might be thinking, it looks like we've only made our lives more complicated, and indeed we have. However, consider what happens when we give the new fact maker a different argument. Substitute high for f. Wait, okay. Gotta test this out. Lambda f, lambda n, if equal n1, 1, n fact maker f, n1. Wait. So this definition is exactly the same as the recursive definition of factorial. I feel like I'm just on the cusp of figuring this out. Hello? Okay. I know I'm jumping around a lot to different pages, by the way. I'm trying to find the thing that clicks, you know? So I came across this longer explanation of Y Combinator, which I also dumped in my list of links on the blog post. And it looked promising, so, because I feel like I need the full, full length treatment, and full schema hasn't quite been gelling, and a lot of other stuff I looked at hasn't been gelling, but maybe this will. So this guy says he wrote a blog post about Y Combinator. He got useful comments, so he wanted to expand it. He says there's not a lot of practical utility to learning about it, but it's a beautiful idea, and it shows how powerful simple ideas of functional programming can be. It mentions that Paul Graham named Y Combinator the company for Y Combinator the idea. So he starts with factorials, which the video I was looking at earlier also did. So we'll start our exploration of the Y Combinator by defining some functions to compute factorials. The factorial of a non-negative integer n is the product of all integers starting from 1 and going up to and including n. Thus we have factorial 1 equals 1, 2 equals 2 times 1, 3 equals 3 times 2 times 1, which is 6, factorial 4, yada yada. And he says I'm using a function notation without parentheses here, so factorial 3 is the same as what is usually written as factorial parentheses 3. Humor me. Factorials increase very rapidly with increasing n. the factorial of 20 is this number. The factorial of 0 is defined to be 1. This turns out to be the appropriate definition for the kinds of things factorials are actually used for, like solving problems in combinatorics. It's easy to write a function in a programming language to compute factorials using some kind of looping construct, like a while or for loop in C or Java. However, it's also easy to write a recursive function to compute factorials because factorials have a very natural recursive definition. Factorial 0 equals 1, factorial n equals n times factorial of n minus 1, where the second line applies for all n greater than 0. In fact, in the computer language Haskell, that's the way you actually define the factorial definition in Scheme, the language we'll be using here. This function would be written like define factorial n if n equals 0, return 1, otherwise multiply n by the factorial of n minus 1. So he talks about the notation Scheme uses. And meanwhile, I said it looked promising because I'm very familiar with the notation. And I think when you're already having trouble with a concept and then the notation is unfamiliar, it's like, oh God, this is like, it becomes too much to deal with at the same time. It's like, you can't learn a new notation while you're struggling at the absolute limits of your conceptual capacity at the same time. Like, that, it doesn't work right. So the keyword lambda, by the way, just as a tangent. So if I can't figure out things from something that uses notation that I'm already familiar with, one option I could do is like learn some additional notation and then look at stuff in that notation. Like that would be a way forward if that winds up being the case. So the keyword lambda simply indicates the thing that we're defining. That is, whatever is enclosed by the open parentheses to the immediate left of the lambda and its corresponding closed parentheses is a function. What comes immediately after the word lambda in parentheses are the formal parameters of the function. Yeah, I like that he's laying everything out. Like, it's like, yeah, I know that, but like, it's good. Like, let's really get everything step by step, Here there is just one argument, which is n. The body of the function comes after the formal arguments, and here consists of the expression, and you see the definition of factorial. This kind of function is an anonymous function. Here you do give the anonymous function the name factorial after you've defined it, but you don't have to. And often it's handy not to if you're only going to be using it once. In Scheme and some other languages, anonymous functions are often called lambda expressions. Scheme programming languages, or many programming languages besides Scheme, allow you to define anonymous functions, including Python, Ruby, JavaScript, OCaml, and Haskell, but not C, C++, or Java, unfortunately. I'll be using lambda expressions a lot below. In the Scheme language, the definition of factorial just given is identical to the one before it. Scheme simply translates the first definition into the second one before evaluating. Yeah, so that I know. This way of writing define is just like a shortcut for them. So all functions in Scheme are really lambda expressions, right? Note that the body of the function has a call to the factorial function, which we're in the process of defining inside it, which makes it a recursive definition. I will call this kind of definition where the name of the function being defined is used in the body of the function an explicitly recursive definition. You might wonder what an implicitly recursive function would be. I'm not going to use that expression, but the notion I have in mind is a recursive function which is generated through non-recursive means. Keep reading. For the sake of argument, we're going to assume that our version of Scheme doesn't have the equivalent of for or while loops in C or Java, although in fact real Scheme implementations do have such constructs, but under a different name. So that in order to define a function like factorial, we pretty much have to use recursion. Scheme is often used as a teaching language, partly for this reason. It forces students to learn to think recursively. Functions as data and higher order functions. Scheme is a cool language for many reasons, but one that is relevant to us here is that it allows you to use functions as first-class data objects. This is often expressed by saying that Scheme supports first-class functions. This means that in Scheme, we can pass a function to another function as an argument. We can return a function as the result of evaluating another function applied to its arguments, and we can create functions on the fly as we need them using lambda notation shown above. This is the essence of functional programming and will feature prominently in its own discussions. Functions which take other functions as arguments and/or, which return other functions as the results, are usually referred to as higher order functions. Now here's the puzzle. What if you were asked to define the factorial function and scheme, but were told that you cannot use recursive function calls in the definition? For instance, in the factorial function given above, you cannot use the word factorial anywhere in the body of the function. However, you are allowed to use first-class functions and higher-order functions any way you see fit. With this knowledge, can you define the factorial function? The answer to this question is yes, and it will lead us directly to the Y Combinator. The Y Combinator is a higher-order function. It takes a single argument, which is a function that isn't recursive. It returns a version of the function which is recursive. We will walk through this process of generating recursive functions from non-recursive functions using Y in great detail below, but that's the basic idea. A higher order function, which takes a non-recursive function and returns a version of the function which is recursive. That's pretty cool. And so the higher order function would be like make length or make fact, probably, that we've seen before. More generally, Y gives us a way to get recursion in a programming language that supports first-class functions, but doesn't have recursion built into it. So what Y shows us is that such a language already allows us to define recursive functions, even though the language definition itself says nothing about recursion. This is a beautiful thing. It shows us that functional programming alone can allow us to do things that we would never expect to be able to do. And it's not the only example of this. Lazy restrict evaluation. We'll be looking at two broad classes of computer languages, those that use lazy evaluation and those that use strict evaluation. Lazy evaluation means that in order to evaluate an expression in the language, you only evaluate as much of the expression as is needed to get the final result. So if there is a part of the expression that doesn't need to get evaluated, it won't be evaluated. In contrast, strict evaluation means that all parts of an evaluation will be evaluated completely before the value of the expression as a whole is determined, with some necessary exceptions such as if expressions, which have to be lazy to work properly. In practice, lazy evaluation is more general, but strict evaluation is more predictable and often more efficient. Most programming languages use strict evaluation. Haskell uses lazy. We'll use both kinds of evaluation on what follows. Well, one Y Combinator or many. Even though we often refer to Y as the Y Combinator, in actual fact there are an infinite number of Y Combinators. We will only be concerned with two of these, one lazy and one strict. We need two Y Combinators because the Y Combinator we define for lazy languages will not work for strict language. The lazy Y Combinator is often referred to as a normal order Y Combinator, and the strict one is referred to as the applicative order Y Combinator. Basically, normal order is another way of saying lazy, and applicative order is another way of saying strict. Another big dividing line in programming languages is between static and dynamic typing. Statically typed language is one where the types of all expressions are determined at compile time, and any type errors cause the compilation to fail. A dynamically typed language doesn't do any type checking until runtime, and if a function is applied to arguments of invalid types, for example, by trying to add together an integer and a string, then an error is reported. C, C++, and Java are statically typed, and Perl, Python, and Ruby are dynamically typed. Scheme is also dynamically typed. There are other languages that straddle the border, but I won't discuss this further. One often hears static typing referred to as strong typing and dynamic typing referred to as weak typing, but this is an abuse of terminology. Strong typing simply means that every value in the language has one and only one type, whereas weak typing means that some values have multiple types. So scheme, which is dynamically typed, is also strong typed, whereas C, which is statically typed, is weakly typed, because you can cast a pointer to one kind of object into a pointer to another type of object without altering the pointer's value. I will only be concerned with strongly typed languages here. Okay. It turns out to be much simpler to define what the Y Combinator in dynamically typed languages, so what I'll do. It is possible to define a Y Combinator in many statically typed languages, but at least in the examples I've seen, such definitions usually require some non-obvious type hackery because the Y Combinator itself doesn't have a straightforward static type. That's beyond the scope of this article, so I won't mention it further. What a combinator is. A combinator is just a lambda expression with no free variables. We saw above what lambda expressions are. They're just anonymous functions. But what's a free variable? It's a variable, i.e. a name or identifier in the language, which isn't bound variable. Happy now? No. Okay. So let me explain. A bound variable is simply a variable which is contained inside the body of a lambda expression that has that variable name as one of its arguments. So a bound variable is simply a variable which is contained inside the body of a lambda expression. Are the variables in the body of these lambda expressions free variables or bound variables? We'll ignore the formal arguments of the lambda expressions because only variables in the body of the lambda expression can be considered free or bound. So for the other variables, here are the answers. The x in the body, so for number 1, the x in the body, which is this one, of the lambda expression is a bound variable because the formal argument of the lambda expression is also x. The lambda expression has no other variables, therefore it has no variables, therefore it is a combinator. So a bound variable is simply a variable. Let me scroll up so I don't see the rest of these because I want to try and figure this out. So a bound variable is simply a variable which is contained inside the body of a lambda expression that has that variable name as one of its arguments. So if the lambda expression has the variable name as one of its arguments and the variable appears in the body, then it's bound. So x is an argument to lambda because that's what this means. And it appears in the body. So it's a bound variable. There's only one variable. So there's no free variables. So this is a combinator. Y appears in the body. It's not an argument to the lambda. There are no other variables to consider. So y is a free variable. So this is not a combinator. Okay, now this is getting more tricky. So this lambda takes y as an argument. X appears in the body, but is not an argument to the lambda. There's no other variables to consider. So it's a free variable. So then does that make this whole thing not a combinator? Oh, it is a combinator. Okay. Okay, so you consider the lambda as a whole. Okay, that's a bit tricky. Oh, I see. So you only consider, it says, we'll ignore the formal arguments of the lambda expressions because only the variables in the body of the expression can be considered free or bound. And then you're also looking at the, so for the free or bound question, we only ask it of the stuff that appears in the body. So we wouldn't consider y, we just consider x. We see it's bound by the outer lambda, so then there's no free variables, so it's a combinator. So then for number 4, we consider both x and y because they both appear. X is bound by the outer lambda, y is bound by the inner lambda, so there's no free variable, so it's a combinator. Okay. Aside from the formal arguments of the lambda expression, there are 2 variables. The final x and y both bound variables, so this is a combinator. So this x, it's not in the body of the lambda expression, so only variables in the body of the lambda expression can be considered free or bound. So we would only consider the y, it's bound, so this is a combinator? It seems counterintuitive for some reason. Oh, the entire expression is not a lambda expression. Oops, I read too far. So by definition, it's not a combinator. Nevertheless, x is the free variable and y, the final y is a bound variable. Oh, and again, this is outside of the lambda, so it's not a combinator. Okay. When you're wondering if a recursive function like factorial is a combinator, you don't consider the defined part. What you're really asking is if it's a combinator. Since this is a lambda expression, the name factorial represents a free variable. The name factorial is not a formal argument of the lambda expression. This is not a combinator. This will be important below. I see. So the name factorial represents a free variable. The name factorial is not a formal argument of the lambda expression. In fact, the names equals, multiply, and subtract are also free variables. Why are they free variables? Well, a variable is a name or identifier in the language. And a bound variable is a variable contained inside the body of the lambda expression that has a variable name as one of its arguments. So these are all things that aren't formal arguments, but are names and identifiers. They're not formal arguments of the lambda, only n is, but they are names and identifiers. In fact, yeah. So even without the name factorial, this would not be a combinator. So a combinator is a really limited thing. Abstracting out the recursive function call. Recall the factorial function we had previously. Lambda n, yeah. What we want to do is to come up with a version of this that does the same thing, but that doesn't have that pesky recursive call to factorial in the body of the function. Where do we start? It would be nice if you could save all of the function except for the offending recursive call and put something else there. This might look like, right, it's question mark. This still leaves us with the problem of what to put in the place marked question. It's a tried and true principle of functional programming that if you don't know what you want to put somewhere in a piece of code, just abstract it out and make it a parameter of a function. The easiest way to do this is as follows. Almost factorial. So takes an argument f. So we've seen this a couple times now. Takes an argument f and puts that f in the body of this, lambda. What we've done here is to rename the recursive call factorial to f and to make f an argument to a function which we're calling almost factorial. Notice that almost factorial is not at all the factorial function. Instead, it's a higher order function which takes a single argument f, which had better be a function, or else f of n minus 1 won't make sense, and returns another function, the lambda n part, which hopefully will be a factorial function if we choose the right value for f. It's important to realize that this trick is not in any way specific to the factorial function. We can do the exact same trick with any recursive function. For instance, consider a recursive function to compute Fibonacci numbers. The recursive definition of Fibonacci numbers is as follows. 0 equals 0, 1 equals 1, or Fibonacci 0 equals 0, Fibonacci 1 equals 1, Fibonacci n equals Fibonacci n minus 1 plus Fibonacci n minus 2. In scheme, we can write the function this way. Define Fibonacci lambda. Yeah, that makes sense. Arcana is just a shorthand for nested if expression. We can then remove the explicit recursion like we did for factorial. Right, yeah, I see how that's the same. That's pretty straightforward. As you can see, the transformation from a recursive function to a non-recursive almost equivalent is purely a mechanical one. You rename the recursive function inside the body of the function to f, and you wrap a lambda f around the body. If you follow what I just did, never mind why I did it, we'll see that later, then congratulations. Okay, as Yoda says, you've taken the first step into a larger world. Cool. Probably shouldn't do this yet, but I'm going to give you a sneak preview of where we're going. Once we define the y combinator, we'll be able to define the factorial function using almost factorial as follows. Define factorial y almost factorial, where y is the y combinator. Note that this definition of factorial doesn't have any explicit recursion in it. Similarly, yeah, I see that because we've got factorial and almost factorial and y, but there's no direct like calling itself. Note that this definition of factorial, yeah, I already read that. Similarly, we can define Fibonacci function using an almost Fibonacci the same way. Define Fibonacci, y almost Fibonacci. So the y combinator gives us recursion whenever we need it, so long as we have the appropriate almost function available. The almost function being a higher level function that you provide, i.e. the non-recursive function derived from the recursive one by abstracting out the recursive function calls. We don't see what's really going on here and why this will work. Now, covering factorial from almost factorial. Let's assume, for the sake of argument, that we already had a working factorial function lying around, recursive or not, we don't care. We call that hypothetical factorial function factorial a. Now consider the following. Define factorial b almost factorial a. Question, does factorial b actually compute factorials? To answer this, it's helpful to expand out the definition of almost factorial. Define factorial b lambda f lambda n. So almost factorial is this part. This represents, and then this part represents almost factorial being invoked with the argument factorial a, and then this whole thing is the expansion of, and try substituting factorial a for f. So if we do this, and we're assuming factorial a is a working factorial function we have somehow, then this is what we get as a result. And he says, this looks a lot like the recursive factorial function, but it isn't. Factorial a is not the same function as factorial b. So it's a non-recursive function that depends on a hypothetical, non-recursive function that depends on a hypothetical factorial a to work. It looks like a recursive factorial function, but we're stipulating that factorial b and factorial a are different. Factorial a is just something we have that magically works. Does it actually work? It's pretty obvious it should work for n equals 0. If it's factorial b, we'll just return 1, the factorial of 0. If n is greater than 0, then the value of factorial b n will be n times factorial a of n minus 1. Now we assume that factorial A would correctly compute factorials. So factorial A, n minus 1, is the factorial of n minus 1, and therefore the n times factorial n minus 1 is the factorial of n by the definition of factorial, thus proving that factorial B computes the factorial function correctly as long as factorial A does. So this works, assuming A works. The only problem is that we don't actually have a factorial A lying around. Now, if you're really clever, you might be asking yourself whether we can just do this. We define factorial A in terms of almost factorial A. The idea in this is, let's just assume that factorial A is a valid factorial function. Then if we pass it as an argument to almost factorial, the resulting function will have to be a valid factorial function. So why not just name that function factorial A? It looks like you've created a perpetual motion machine, or perhaps I should say perpetual calculation machine, and there must be something wrong with this definition, mustn't there? M to n if equals n 0, 1, otherwise multiply n minus 1. They say if you use Dr. Scheme as your scheme interpreter, which you should, which you should, then you can use the lazy scheme language level and the above code will actually work. We'll see why below, but for now I want to stick to a standard strict scheme approach and approach the problem in a slightly different way. Let's try a couple of functions. Define identity, lambda xx, define factorial 0, almost factorial identity. The identity function is pretty simple. It takes a single argument and returns it unchanged. So Combinator, as I hope you can tell, we're basically going to use it as a placeholder. When we need to pass a function as an argument, we don't know what function we should pass. Factorial 0 is more interesting. It's a function that can compute some but not all factorials. Specifically, it can compute the factorials up to and including the factorial of 0, which means it can only compute the factorial of 0, but you'll soon see why I describe it this way. Let's verify that. All right, so we invoke factorial 0 with 0, which is going to return almost factorial with the argument identity. Going to return the procedure almost factorial with argument identity on our 0. It does so. So we then return that almost factorial procedure, which then gets past the 0 and equals 0, or 0 equals 0, so it returns 1, and then that's it. So it works. Unfortunately, it won't work for n is greater than 0. For instance, if n is equal to 1, then we'll have factorial 1, right? So it'll be n equals 1, so it goes to the alternative, and it tries to evaluate 1 times the result of calling identity on 1 minus 1. Identity minus 1 minus 1 would be 0, and we get 0. Right, so it evaluates, but it gives us the wrong answer. Now consider this spiffed up version of factorial 0, which is the same thing as, right, so factorial 1 expands to this, and it'll get the right answers for factorial 0 and 1. Right, it'll work because for the 1 case, because instead of identity, like for n minus 1, I'll say, okay, well, it's not 0. I'm sorry, yeah. For n is 1, it'll say, okay, well, n isn't 0, so then 1 times, let's see how he showed it. So, what's factorial 0, 1. So factorial 0, for factorial 0, identity is the f that goes where the, it's what replaces the recursive call. But for factorial 1, factorial 0 is what replaces the factorial call. And so when you have that, if n minus 1, it's not 0, so you multiply that n minus 1 times factorial 0 of n minus 1, which is 0, which is 1. And factorial of 1 is 1, and so that's the right answer. And if you had factorial 2, you would do the same thing. So factorial, so you'd have 2, which is not 0. So then you go to else and you'd say 2 times 2 times factorial 1 of n minus 1. So it'd be 2 times factorial 1 of n minus 1, which is 1, which would be 1. And then we'd have factorial, we'd start building up a chain of like 2 times 1 times factorial of 1 minus 1, which would be 0, or factorial 0 of 1 minus 1, which would be 0, which would again be 1. So then we'd have 2 times 1 times 1, which would be 2, which would be the right answer for factorial 2. Ooh, okay. But then if we try to use factorial 1 for to calculate factorial, if we try to use the factorial 1 procedure to calculate the value of factorial 2, we'll hit actually using the identity argument before we're finished calculating, and that'll throw everything off and give the wrong answer. We can keep going and define functions which can compute factorials up to any particular limit, right? So you keep going. You define factorial n plus 1 in terms of almost factorial n. Basically, it just keep going forever. That factorial 2 will compute factorials for inputs between 0 and 2. Factorial 3 will compute. And so one thing I want to note is that you never want to use identity. Like, you need it as, what do you need it as? You kind of need it to get the whole chain started, but you never actually want it to get invoked, or else it breaks everything. Factorial 2 will compute factorials for inputs between 0 and 2. Factorial 3 will compute correct factorials for inputs between 0 and 3, and so on. You should be able to verify this for yourself using the above derivations as models, though you probably won't be able to do this in your head. One interesting way of looking at this is that almost factorial takes a crappy factorial function and outputs a factorial function that is slightly less crappy, in that it will handle exactly one extra value of the input correctly. Note that you can again rewrite the definitions of factorial functions like this. Note that you can again, right, you just build an increasing tower, and so on. Again, if you're very clever, you might wonder if you could do this, where the ellipses means you're repeating the chain of almost factorials an infinite number of times. Unfortunately, we can't write this out directly, but we can define the equivalent of this. Note that also that factorial infinity is just the factorial function we want. It works on all integers greater than or equal to 0. What we have shown is that if we could define an infinite chain of almost factorials, that would give us the factorial function. Another way of saying this is that the factorial function is the fixed point of almost factorial, which is what I will explain next. The notion of a fixed point should be familiar to anyone who has amused themselves playing with a pocket calculator. You start to hit 0 and hit the cosine key repeatedly. What you find is that the answer rapidly converges on a number which is approximately 0.73 yada yada. Hitting the cosine key again doesn't change anything because cosine that thing equals that thing. We say that the number, that thing, is a fixed point of the cosine function. The cosine function takes a single input value, a real number, and produces a single output value, also a real number. The fact that the input and output of the function are the same type is what allows you to apply it repeatedly. So that if x is a real number, we can calculate what cos of x is. And since that will also be a real number, we can calculate what cos of x is, and so on. The fixed point is the value x where cos of x equals x. Okay, that's straightforward. Fixed points don't have to be real numbers. In fact, they can be any type of thing, as long as the function that generates them can take the same type of thing as input as it produces as output. Most importantly for our discussion, fixed points can be functions. If you have a higher order function like almost factorial that takes in a function as its input and produces a function as its output, with both input and output functions taking a single integer argument as input and producing a single integer as output, then it should be possible to compute its fixed point, which will naturally be a function which takes a single integer argument as input and produces a single integer argument as output, or produces a single integer as output. That fixed point function will be the function for which fixed point function equals almost factorial fixed point function. By repeatedly substituting the right-hand side of that equation into fixed point function on the right, so since fixed point function equals almost factorial fixed point function, you take this and substitute it for this, and then you get that and on to infinity. Okay, that makes sense. As we saw above, this will be the factorial function we want. Thus, the fixed point of almost factorial will be the factorial function. Factorial equals almost factorial factorial. It's all well and good, but just knowing that factorial is the fixed point of almost factorial doesn't tell us how to compute it. Wouldn't it be nice if there was some magical higher order function that would take as its input a function like almost factorial and it would output its fixed point function, which in that case would be factorial? Wouldn't that be freaking sweet? That function exists, and it's the y combinator. Y is also known as the fixed point combinator. It takes a function and returns its fixed point. Okay, time to derive y. Let's start by specifying what y does. Yf returns the fixed point of f. I want to review this a bit as I kind of turboed through it. So the fixed point is the value where x is the value x where cos of x equals x. They don't have to be real numbers. In fact, they can be any type of thing as long as the function that generates them can take the same type of thing as input as it produces as output. So if you have a higher order function like almost factorial that takes in a function as input and produces a function as its output, it should be possible to compute its fixed point, which would be the value where almost factorial of x equals x. What we have shown is that we could define an infinite chain of almost factorials that would give us a factorial function. Another way of saying this is that the factorial function is the fixed point of almost factorial. Wouldn't it be nice if there was some magical higher order function that would take as its input a function like almost factorial, and this is a function that takes functions as arguments, and would output its fixed point function, which in that case would be factorial. So the function that would allow us to use factorial to build a recursive. I'm a little fuzzy on this, but I think I get the idea. It's a lot of concepts. Eliminating most explicit recursion. Okay, time to derive y. So y of f equals fixed point of f. So what do we know about fixed point of f? We know that f fixed point of f equals fixed point of f, right? So f is the almost factorial function. Y is the magic procedure that takes the almost factorial function and outputs the fixed point. And fixed point is the actual recursive procedure that we want. And we've already said that the almost factorial, if we gave almost factorial the fixed point function that is going to be what y generates, then we would get the fixed point, which is the recursive procedure that we want. So y of f equals fixed point of f equals f of fixed point of f. Yeah, that looks right. Therefore, we can substitute y of f for fixed point of f. Y of f equals f of y of f. Okay. If we want it to be expressed in a seam function, we'd have to write it like this. Define y of f of y of f, or using explicit lambda as define y lambda f of y of f. However, there are two caveats. It will only work in a lazy language. It is not a combinator because the y in the body of the definition is a free variable, which is only bound once the definition is complete. In other words, we couldn't just take the body of this version of y and plop it in wherever we need it, because it requires a name y to be defined. Nevertheless, if you're using lazy scheme, you can indeed define factorials like define y lambda f of y of f, and f lambda m. As if you're using lazy scheme, you could do this and it will work correctly. What have we accomplished? We originally wanted to be able to define the factorial function without using any explicit recursive functions at all. We've almost done that. Our definition of y is still explicitly recursive. However, we've taken a giant step because this is the only function in our language that needs to be explicitly recursive in order to define recursive functions. With this version of y, we can go ahead and define other recursive functions, for instance, defining Fibonacci as y almost Fibonacci. I said above that the definition of y that we derived wouldn't work in a strict language like standard scheme. In a strict language, we evaluate all the arguments to a function before calling the function to its arguments, whether or not those arguments are needed. So if we have a function f and we try to evaluate y of f using the above definition, you can get like an infinite expansion. Okay. The evaluation of y f will never terminate, so we never get a usable function out of it. This definition of y doesn't work for strict languages. However, there's a clever hack that we can use to save the day and define a version of y that will work in strict languages. The trick is to realize that y of f is going to become a function of one argument. Therefore, this equality will hold. Y of f equals lambda of x, y of f of x. Whatever one argument function y f is, lambda x, y of f of x Has to be the same function. All you're doing is taking a single input value x and giving it to the function defined by yf. In a similar way, this will be true. Cos equals lambda of x cosine of x. It doesn't matter whether you use lambda, whether you use cosine or lambda x cosine x as your cosine function, they'll both do the same thing. Let me back up. The trick is to realize that y of f is going to become a function of one argument, y. I'm just going to read on a bit. Turns out that lambda x y of x has a big advantage when defining y in a strict language. By the reasoning given above, we should be able to define y as follows. Define y lambda of f of lambda of x, and then y of f of x. Since we know that this is the same function as y of f, this is a valid version of y which will work just as well as the previous version, even though it's a bit more complicated and perhaps a tiny bit slower. You could use this version of y to define the factorial function, and it would work fine. The cool thing about this version of y is that it will work in the strict language. The reason for this is when you give y a particular f to find the fixed point of, it will return yf equals f of lambda x yfx. This time there's no infinite loop because the inner yf is kept inside a lambda expression where it sits until needed. Since the body of a lambda expression is never evaluated in the scheme until the lambda expression is applied to its argument. Basically, you're using the lambda to delay the evaluation of yf. So if f was almost factorial, we would have this. We have defined almost factorial, right, that's just almost factorial. And then we define factorial in terms of y almost factorial. Expanding out the call to y, we have lambda f, we have this lambda, which takes the almost factorial as the argument, as an argument, the lambda of f, and then we have the inner lambda, right? And so then the next step is, so then we've got that almost factorial in there, we've substituted it for that f, and also, so we've passed in that almost factorial as an argument, we've substituted it, and now we're expanding the almost factorial. So that's the body, right? This thing. But instead of the f, we have this lambda, which invokes the y combinator on almost factorial. I'm not sure, what does x represent here again? I'm not 100% sure. Here again, lambda x y almost factorial x is the same function as y almost factorial. Oh yeah, there was that identity earlier. Man, this is pretty dense. Which is the fixed point of almost factorial, which is just a factorial function. However, y almost factorial and lambda in this form won't be evaluated until the entire lambda expression is applied to its argument, which won't happen until later, or not at all until a factor of 0. Therefore, this factorial function will work in a strict language, and the version of y used to define it will also work in a strict language. I realize that the preceding discussion and derivation is non-trivial, so don't be discouraged. At this point, we want to not just define y, but a y combinator. Note that the previous lazy definition of y is a valid definition of y, but is not a y combinator, since the definition of y refers to y itself. In other words, this definition is explicitly recursive. A combinator isn't allowed to be explicitly recursive. It has to be a lambda expression with no free variables, as I mentioned above, which means it can't refer to its own name, even if it has a name in its definition. If it did, the name would be a free variable in the definition, as we have in our definition of y. Note that y in this definition is free. It isn't the bound variable of any lambda expression, so this is not a combinator. Another way to think about this is you should be able to replace the name of a combinator with its definition everywhere it's found and have everything still work. Can you see why this wouldn't work with the explicitly recursive definition of y? You would get it into an infinite loop, and you'd never be able to replace all the y's with their definition. So whatever the y combinator will be, it will not be explicitly recursive. From this non-recursive function, we will be able to define whatever recursive functions we want. I'm going back a bit to our original problem. I'm going to go back a bit to our original problem and derive a y combinator from the bottom up. After I've done that, I'll check to make sure it is a fixed point combinator like the versions of y I've already seen. Recall our original recursive factorial function. Recall that we want to define a version of this without the explicit recursion. One way we could do this is to pass the factorial function itself as an extra argument when we call the function. Note that part factorial is not the same as the almost factorial function described above. we would have to call this part factorial function in a different way to get it to compute factorials. Wait a second. To recall that we want to define a version of this without the explicit recursion. So we could pass the factorial function itself. So we basically, we define factorial, but then as one of the formal parameters to factorial, we have a self argument with which we intend to pass the function to itself. Okay, that's a little trippy, but okay. This is not explicitly recursive because we send along an extra copy of the part factorial function as a self argument. Okay, I could see that. However, it won't work unless the point of recursion calls the function the exact same way. Wait, why is there this extra self? Oh, I see. Because you have to say, because we're trying to not have it be explicitly recursive. So we need to have both it as like the name and as the argument. Okay, I got it. Woo. Okay. We can move back to something closer to our original version by rewriting it like this. Let's see what we have here. Part factorial self, lambda n equals 0, 1, yeah. Otherwise, oh, I see. So it's just a slightly different way of invoking it. Oh, I see. They're trying to make it that you can invoke it in the same way. Pause for a second here. Note that we've already defined a version of the factorial function without using explicit recursion everywhere. This is the most crucial step. Right. Okay. So by passing in the function as an argument and then using that argument function twice in the body, you get to avoid explicit recursion. Huh. Okay. I think I'm following. Now let's get back to something like our almost factorial function by pulling out the self-self call using a let expression outside the lambda. So we're defining part factorial self. And right. And so they've defined, so just backing up. So they've defined factorial in terms of part factorial invoked with part factorial as, okay. They define part factorial. Then they define factorial in terms of part factorial with part factorial as the argument. And then you can use factorial with the argument 5, and there's no explicit recursion anywhere. Okay. And now they're just refining. So they're like, well, let's let f be the self-self, and then we still do that definition of factorial in terms of part factorial, and yeah, this will work fine in a lazy language. In a strict language, the self-self call in let will send us into an infinite loop, because in order to calculate part factorial, you'll first have to calculate, oh, hang on. In order to calculate part factorial in the definition of factorial, you'll first have to calculate part factorial in the let expression. Okay. For fun, figure out why this wasn't a problem in the previous definition. I'm not sure. I'll let this go for now because I want to define the lazy y combinator, but in the next section I'll solve the problem the same way we solved it before, by wrapping a lambda around the self-self call. Note that in a lazy language, the self-self call in the let statement will never be evaluated unless f is actually needed. For instance, if n equals 0, then f isn't needed to compute the answer, so self-self won't be evaluated. Understanding how lazy languages evaluate expressions is not trivial, so don't worry if you find this a little confusing. Turns out that any let expression can be converted into equivalent lambda expression by using this equation. Let x expression 1, expression 2 is lambda x, expression 2, expression 1. Expression 1 and expression 2 are arbitrary scheme expressions. I'm only considering let expressions with a single binding and lambda expressions with a single argument, but the principle can easily be generalized to lets with multiple bindings and lambdas with multiple arguments. This leads to, so this returns a procedure, takes a function as an argument, and substitutes it into the body of this procedure, which takes an n as an argument. And as an argument to this procedure, we provide self-self, which is the second argument, or really, no, the only argument to our definition of part factorial. So then when we invoke part factorial, the first argument to it, it may not run, it's not lazy. Yeah, it just runs forever. Okay. But yeah, we get a procedure back that has part factorial substituted in the body here twice. Okay. If you look closely, you'll see that we have our old friend, the almost factorial function embedded inside the part factorial function. Pull it outside, and they have almost factorial. So then they define part factorial in terms of almost factorial invoked with self-self. I don't know about you, but I'm getting fed up with the whole part factorial thing. We define part factorial in terms of a lambda, takes an argument self, returns a procedure, almost factorial, that invokes that argument twice and substitutes it in. Then I can rewrite the factorial function like this. And we still have part factorial. So I don't know. All right, I was following this for a while, but now I feel like I'm losing the plot again. So I'm wondering, though, if there's one thing I'm not getting, which is why they're calling everything make length here. Let's reread this part. I figured out, like, I think I understood some of this from the web page. So I'm seeing if I can jump back to the little schemer and see if I can make any progress on that. So this made sense, the infinite tower. Do we really need an infinite tower? Not really, of course. Every time we use length, we only need a finite number, but we never know how many. Could we guess how many we need? Sure, but we may not guess a large enough number. When we do find out that we didn't guess a large enough, when do we find out that we didn't guess a large enough number? When we apply the function eternity that is passed to the innermost make length. So that's like the identity that we never want to run on this page. What if we could create another application of make length to eternity at that point? That would only postpone the problem by one, and besides, how could we do that? Well, since nobody cares what function we pass to make length, now why does nobody care? Is it because we never want to run it? Like, that's not really explained very well. Yes, we could even use make length instead of length. Why would we want to do that? All names are equal, but some are more equal than others. Like this just seems really confusing to me without a lot of explanation. It's like make length again, you know? Like, I don't think they established the groundwork for this making a lot of sense. All right, I think I'll take another stab at this later. Okay, so found another blog post, recently updated, and the guy, it's a guy, yeah, Peter, based his discussion of Y Combinator on little schemer. So he's using scheme, he's using that notation, and he says, I took the examples from the book, filled in the missing steps, and explained the steps in more details. So hopefully this will be good. And he says, the Y Combinator allows an anonymous function to call itself. That is, it allows anonymous function recursion. Since anonymous functions don't have names, they can't refer to themselves easily. The Y Combinator is a clever construct that helps them to refer to themselves. That's it. That's all the Y Combinator does. Remember that. Okay. So suppose we want to write the length function, which, given a list, returns the number of elements in it. It's really easy if we can give the function a name. Yeah, I've been able to do that for years. But now suppose that we can't give names. We can only use anonymous functions, or lambdas. So then we've got lambda list cond null list. Probably shouldn't use list as an argument because that's also a function, but that's okay. But anyways, yeah, so then instead of length, we've got question mark. Suddenly there is no way this anonymous function can refer to itself. What do we put in question mark? We can't refer to the name length anymore because it's an anonymous function which doesn't have any name. Right, this function representing length is now unnamed. One thing we can try is to put the function itself in place of question mark. So in other words, where question mark is, we just dump the whole thing, we like copy paste it and stick it in there. Okay, that is not much better. We are still left with question mark, yeah. But there's a bright side. This function can determine the lengths of lists with one element and no elements. Right, this is a thing we've seen a few times where it's like, well, if you just keep building up this chain, you don't get full recursion, but if you want to keep stacking these procedures, you can get to any arbitrary length that you're willing to stack the lambdas on top of each other. But you still, you don't solve the problem of creating like the general purpose recursive procedure. You just have a bunch of stacked lambdas that can go to, length 287 or however, wherever you lose your patient. This is not much better way to still have a question mark, but there's a bright side to it. This function can determine the lengths of lists with one element, no elements. Let's try inserting the same function, the same anonymous function in place of question mark again. And we've got it stacked 3, so now we can go up to 2 elements. If we continue this way, we can construct length function for lists with a certain number of elements, but this is not what we want. We want the real length function. It works for lists with any number of elements. As we all know, repeating code is not a good thing. Let's try to factor out the repetitions and rewrite the original anonymous function slightly. Instead of leaving question mark in the code, let's pass it to an anonymous function via an argument called length. Right, so then now we're taking length, a length procedure. Length is an argument for this lambda that stands where we provided this procedure. We don't know what it is yet. And it substitutes that procedure into the body of this here. Notice that this code invokes the first lambda length function and passes a question mark as the length argument. This function in turn returns the original anonymous function. So after we do all this, after we pass in the question mark function, mystery function x, we get this back, ready to take a list and not do anything with it because we haven't finished the procedure yet. Now let's try constructing the previous 2 length functions that work for lists with a maximum of 1 and 2 elements. First, the function for lists with a maximum of 1 element. So here, question mark first gets passed to lambda g, because that's how this is written. So the function question mark is provided as an argument to lambda g, which returns the original anonymous function, meaning this, which then gets passed to lambda f, which in turn returns the function that works for lists with 1 element. So you see how this whole original function gets substituted in where the question mark was. Similarly, the following code returns a function that works with a maximum of 2 elements, right? So h is going to get passed question mark, return a function. You could call it length 0 if you want to give it a name. So length 0 goes here in the g function, which is going to return a function, which is going to return length 1. Length 1 is going to go here. And then by that means, we'll be able to calculate 2 elements. I feel like I'm getting more able to talk about this, at least parts of this, somewhat coherently. I'm still halting on some parts of the problem, but like not completely, not like I'm completely lost and have no idea what's going on whatsoever. It's more just like I'm still trying to fully grasp it. So since the argument names f, g, and h, and lambda f, lambda g, and lambda h are independent, we can rename all of them to length to make it look more similar to the length function. So I think that's important. We are still repeating code. The obvious thing we can do is to create an anonymous function called makeLength that creates this code for us. This is pretty tricky. Yes, this is where I've kept getting stuck. Observe how lambda makeLength gets the lambda length function. Lambda makeLength, etc., gets the lambda length function passed as the makeLength argument, which in turn accepts question mark mystery procedure as an argument and returns our original anonymous function. Okay. Yeah, I don't think I knew what was exactly going on here. What page was that on again? Let's scroll up. Right, so this looks like the closest. Page 165. Yeah. So I mean that makes sense. It's the stacking of lambdas can get confusing. So the first lambda takes the second lambda. Well, hang on. Okay. I'll follow this guy's presentation because it's making more sense to me than the book's presentation. So yeah, the lambda makeLength gets the lambda length function passed as the makeLength argument. So the highest level lambda takes the inner lambda as an argument. So it takes that function as an argument and applies it to a function because the inner lambda takes a function as an argument as well. Woo. Okay, so the inner lambda takes length as an argument. and substitutes, it takes a function as an argument and sticks that function in the body. The higher level lambda takes this whole function as an argument and returns a function. So the higher level lambda takes the inner lambda, or the outer lambda, let me say outer inner, because that's I think that's more conventional and it's easier to say. So the outer lambda takes the inner lambda as its argument make length and returns a procedure which takes a procedure as an argument to substitute into the body of length, into the body of the inner lambda, I should say, in the place where length, is that right? I think that's right. So the outer lambda takes the function this down. I should actually try this out. Oh, this might loop because of the, oh, we have a question mark, so that's not gonna work. Oops. Okay. I don't fully know how it works, but I could still say sensible, true stuff like the outer lambda takes the procedure returned by lambda length as the argument make length. Make length takes a procedure as an argument and substitutes it into the body of the inner lambda procedure lambda list. ... Okay, I think that's true. Now let's try constructing length functions for lists. This is a really important part, and unfortunately he has a like HTML error. But I tried to clean it up. See if I can zoom that. Okay, I think this is right. So let's try constructing length functions for lists of length 1 and 2. For the list of length 1, we just need to apply a make length on itself. Let's go through this code. First, lambda length gets passed to lambda make length function as the make length argument. This gets passed as that. Okay. Then it applies the result of make length question mark, which is the original anonymous function to the make length. So first this function gets passed as an argument, and then, oh, I see. He's trying to color code them, and I wonder if it works in another browser. It's worth at least checking. What the hell? Safari doesn't even want to open the... That's weird. Okay, well, whatever to that. So, recreate this maybe. Okay. Then it applies the result of this, which is the original anonymous function, to the make length. This produces our well-known function that works on lists with one or none element, right? We get a function that, adds 1 to the result of, assuming the list isn't null, so if it's one element, then we add 1 to the result of our original, of our length 0 function. Similarly, by adding another call to make length, we get a function that works with lists of 2 or fewer elements. Right, yeah. Now, since we don't, okay, so this is the part I've gotten stuck on like 5 times now. Okay, since we don't know what the mystery function is, let's just call it make length and see what happens. Okay, I mean, sure. Nothing bad actually happens. We still get the same original anonymous function, except in place of the question marks, we have the function, this function. Notice also that the argument names make length and lambda make length. So notice also that the argument names make length and lambda make length and lambda length are independent. Therefore, we can rename length to make length to remind that the first argument to make length is make length. So I think it's saying these names of these arguments are independent from each other. It's not going to confuse anything within the program if we use the same parameter name within the 2 different lambdas or over here. So we can rename what we were calling length, make length, as a reminder that this argument is now make length. Okay, that's like, sure, I'll go with that. Now here comes the key trick. Replace make length with a self-application. Make length. Yeah, it works. The function works because it keeps adding recursive uses by passing make length to itself just as it is about to expire. Wait, so to get the whole thing rolling, we have this outer lambda that takes make length as an argument. It applies, okay. So the outer lambda takes an argument make length, which is a function, and applies that function to that function. And then within the body of that function that gets returned by that outer lambda, we check if the list that inner lambda function takes is empty. And if it is not, we add 1 to the result of the value returned by applying the makeLength function to the makeLength function and then applying the procedure that's returned by that to the cdr of the list. Is that right? I think maybe that makes sense. The function works because it keeps adding recursive uses by passing makeLength to itself just as it is about to expire. This is not the Y Combinator, but we have successfully managed to recursively call an anonymous function. Now we need to massage the code a bit to separate the anonymous function from the self-applicative code. The first step is to move the self-applicative code out as much as possible. I want to ignore these strong tags because he's trying to bold this part, but it didn't take. Now the code in bold looks very much like the length function we need. Let's move it outside as well. I finally loaded in Safari, but it's the same issue. Okay, let me clean this up a bit. So he says you want to move the self-applicative code out as much as possible, and you notice a difference. So he's redone. So we were saying we're calling this makeLength as well before. He's calling it length, and what he's doing is he's passing in as an argument to this lambda, which is, that's the part he wanted it in bold, yeah. This lambda, he's passing in this lambda as an argument to this lambda. And what it is, so what is he passing in? He's passing in a procedure of one argument that applies makeLength to itself and takes an argument. So I think the operation here is that this gets substituted in there, and so you have makeLength, and then you take the cdr of the list as an argument. So he's so that's what he means by he's abstracting out some of the self-applicative code. So he says now the code in bold, where is that? Looks very much like the length function we need. Let's move it outside as well. And then what does he wind up with? He winds up with that, with this part. There we have it. The anonymous length function has been separated from the self-applicative code. The code in bold is the length function, and the code not in bold is the Y Combinator. Le lambda x. So there's a le that gets introduced. LE. So I see he's moving things around. I see we've got lambda makeLength. I'm not sure where the le came from. That was not explained. But I think I followed this further than any explanation I've seen so far. I mean, I'm looking at a lot of them, right? So like, you'd hope there's some accrual of knowledge happening. We use a name like makeLength that is a constant reminder that the first argument to makeLength is makeLength. Right, okay, so that's consistent with what he said. Now that makeLength is passed to makeLength, can we use the argument to create an additional recursive? Yes, when we apply makeLength to makeLength, we get length less than or equal to 1. What is the value of this? Well, if L is apples, not null, so it's going to be add 1, makeLength eternity with cdr L, which is the empty list. So add 1 to makeLength eternity with the empty list, which we have it, which is going to return 0. So we're going to return 0 and add 1. We do this more than once? Yes, we can just keep passing makeLength to itself, and we can do this as often as we need to. Would you call this function? Is length, of course. Yeah, no, this doesn't look like crazy babble anymore, which I think is good. Like, I certainly couldn't have figured it out on my own, but it's not like, what is this nonsense? How does it work? It just keeps adding recursive uses by passing makeLength to itself just as it is about to expire. One problem is left. It no longer contains the function that looks like length. You could extract this new application to makeLength, this new application of makeLength to itself, and call it length. Oh, I see. They're highlighting. So now in here we have the function that looks like a normal length function, and we're making it work still in the context of not having defined functions, not having a defined length, by passing it as an argument, this like self application of length. One thing I'm not, I'm still a bit confused by using the appearance of make length like 6 times in the procedure, but so what is the value of this stuff where L is apples? It should be 1. They say first we need the value of all this basically. Right, so they're pointing out that if you try to calculate the value of this where L is apples, you keep having to calculate more and more things. Yes, there's no end to it. Why? Because we just keep applying make length to itself again and again and again. Is this strange? It is, because make length used to return a function when we applied it to an argument. Indeed, it didn't matter what we applied it to. But now that we've extracted make length from the function, it makes length from the function that makes length, it does not return a function anymore. No, it doesn't. So what do? Turn the application of make length to itself and our last correct version of length into a function. How? If f is a function of one argument, is lambda x f of x a function of one argument? Yes, it is. So this was the thing that we were reading about earlier. We're wrapping this self-application in a lambda somehow defers the evaluation. Yeah, so the Veneer LiveJournal guy said, the body of a lambda expression is never evaluated in scheme until the lambda expression is applied to its arguments. So with this writing of it, rather than having to need to evaluate the whole expression, because the problem we had before was that we needed to evaluate the value of the entire expression in order to determine the function that we wanted to apply to apples. But I'm guessing that with this writing of it, because lambda doesn't get, what do you say? Because the body of the lambda won't get evaluated until the expression is applied to its arguments, and because we won't need to apply this expression to its arguments when the recursive calls hit, when we get to the empty list, then this will be fine. So then they're just like refactoring the code. So they ask, is it okay to move this function, the application of make length to itself, around so that we can get our length procedure back? And they say, yes, we just always did the opposite by replacing a name with a value. Here we extract a value, meaning this procedure that we're now calling length, and we give it a name. It's going to be its length within the body. Can we extract the function in the box that looks like length and give it a name? Yes, it does not depend on make length at all. So I see that they've pulled apart the actual length procedure from the procedure that makes it. And so then they've got just this procedure that is the procedure. Well, what do you give this procedure? Applicative order Y combinator. So what is LE? I get the general idea of what's going on here, but I'm not sure I follow the details. However, I'm definitely running out of steam on this, so I'm going to wrap it up.